Okay. So
Okay.
good evening. Yeah, good evening to one and all present here. So today we are at virtual talk series. And today we have with us Mr. Anuj Shah. He has pursued his master's in mechatronics and currently working as senior engineer in perception lab of Continental Automotives at Bangalore. And he has 4 years of experience in deep learning. And basically, he has worked on several research projects as well to implement deep learning based solutions in the area of iris recognition, emotion recognition, and also driver perception modeling. So, with this brief introduction, I would like to invite our speaker. And Mr. Anuj, over to you now.
Great. Thank you, Anupama. And very good evening, everyone. I'm glad you guys have joined here. And today, talk series won't be anything related to my work or my company's work. It's basically going to be, since I was told that there will be a lot of students, I'll be trying to maybe open some window to show you some other dimensions beside supervised learning, because it's very easy that we get overwhelmed by the information present on internet. And right now you will get, my myriads of information just regarding supervised learning. So this will be a more of like a tutorial introduction to different approaches that you can take beside supervised learning. And when I say looking beyond supervised learning, I actually mean moving beyond the label data. Okay. So that's me. Yeah, I work at Continental at the Perception Lab. And so basically, you know what the current trend is right now? That we have taken supervised learning for granted. So doesn't matter like whatever problem is given to us, we take this data set, say, and we label it. Just Actually, I'm getting this screenshot. Okay, sorry for that. So usually what you do, you will get a data set, you will label it, say a horses or zebra, then you train it and you're able to predict it. That's the trend. And we should be definitely proud of it, because with the supervised learning, we have been able to, achieve a lot in the industry area, say uh, the Amazon Alexa or Google Home at your home, or the Google Assistant in your phone, or the Netflix or Amazon recommender system that recommends you movie, or your shopping, or in the medical diagnosis, or even in your personal mail where they recommend you what to type next, and umpteen numbers of Google apps that they use supervised learning. So we are glad supervised learning work. It's pretty cool. But today, when we actually say artificial intelligence, what we actually mean is machine learning, and what we actually do is deep learning. And in that, what we actually code out is basically just supervised learning. And this is from Jan LeCun talk, who says that we are too much, concentrated towards supervised learning. Let's get a bit diversified. So before I start my talk, so this is my face, okay? And I'm just showing with my face, and this is another picture of me. Can you guys identify who am I? Say the number like this, guys: 1, 2, 3, 4, 5 from the left. So who would be me? Any guesses? Third? Okay.
You are in there.
Yeah, because Devender knows, because Devender because Devender knows me. But I hope even the people who don't know me, they would be able to recognize the short guy here. The reason being, our brain is so evolved, that just by seeing one picture, it's able to recognize me, or know who am I. And which is not the current trend in the supervised learning. We have to feed them, thousands of images in order to make them do one task. But see our brain, how quickly they recognize us. And yeah, this is a picture from 2016 match between Kings 11 Punjab and I forgot Pune. Yeah, and that's Arshdeep, your yesterday speaker. And yeah, let's move ahead. So again, my goal of today's talk is to open some windows for you so that you can just look around besides supervised learning. So even if I'll not be talking about all this topic, but I'll request the students and the other researchers that you have a look on all these topics as well. Not only get constrained to supervised learning, have a look at self-supervised, unsupervised, semi-supervised, active learning. There are memory augmented networks, there are few shot learning, meta learning, multitask learning. And although the name may look okay daunting, that okay, they're a kind of new technology, but they aren't kind of, they're related. And among these, I'll be speaking on few of the topics. So let's get started. And one more brain trick for you guys. So on the left, there are three images from an artist called Braque, and on the right, there are three images from an artist called Kazane. And this is a test image. Can you guys say which this picture was drawn by which artist? Any guesses? Is it Braque or Kazane? Okay. So, okay, probably you would have guessed this is Braque. And again, that's the power of a brain, that just by seeing few images we are able to, recognize this task. And this is just I'm just showing in context of recognition, and this is this holds in the context of every other task that we do in our real life. Okay, so you would have seen this news, yeah, that AI was able to defeat human guy pretty cool in the game of Go. And Go is a really complicated game. There are uh, as many possible positions in game of Go than there are total number of atoms in known universe. And AI defeating us is really cool. And there's a movie, there's a documentary on AlphaGo. So you go and you go and watch this documentary, how they train this model and all. You'll come to know. And this is another slide. This is pretty old slide, but again you can see here that in the ImageNet challenge recognition, the AI model was able to defeat human, by quite a margin. And these are showing the successes of AI. But again, if you remember your childhood, on the right side is a game of Mario, and I'm pretty sure when you started playing, it would have taken you just a couple of hours or not even that to master this game, to understand that you have to save the princess and how you have to get the points. But when the people who are training Go, they have to train it for hundreds and hundreds of hours. That much training time is required to train such kind of RL models. And also in this case, we were so quick that from just three images we are able to identify the painter. And when coming to the ImageNet, where the AI guy was able to defeat the human, it was because they were trained on 14 million images among 1,000 object classes, and that was the reason they were able to defeat us. But that's not the case. That should not be the case. Intelligence is not about just dumping data and they are able to. Obviously, they are learning, but it should be more like us, that we are able to extract representation, extract information, and then able to use it whenever required to as many tasks as required. So if you see the current scenario of how we train the model, it looks like something like this. We have this data, we have some feed forward, we back propagate, we train it with gradient descent iteratively. But the problem, as I said, it takes a longer time to learn because we are doing a lot of iteration. And also, what happens when new data comes in that scenario, then this network doesn't work because this is task specific, right? The current traditional network that we see is task specific. In that scenario, you have to relearn the parameters in order to incorporate new information. But uh, if you want to say, in the scenario when there is uh, the previous scenario was when there was data, but there will be scenario when there is very less amount of data. For example, say in medical field, consider the COVID-19 cases where the people are taking x-rays. Okay, so the x-ray of infected people is quite less. So in those scenarios when there are less amount of data, can we have some kind of hack, a smart hack, to make the machine learn from it? So that's why we are trying to explore all these new technologies. Now, I'll try to give you one more scenario. So, how human learns from the small data. Say, this is a word called nincompoop. Many you might be knowing the meaning of the word, but if you don't know, it means stupid or foolish. Now, I just showed you one instance of this word, just one, and now you will be able to use this in so many contexts. In context of noun, in context of pronouns, in say in Hindi language also you can use it. So just by one example, you understood it context, and you can use in so many variety of tasks. That's how we learn. And take another example. There is a wood, and I give you a lot of tools like axes and saw, and I ask you collect as many fruits as you want. You may never been to woods, okay? You may never done cutting and carpentry, but by default, your brain will somehow figure out that first I need to cut the woods, I need to make the planks, I need to make the box, and there I need to store the fruits. Nobody taught you this, but somehow we are able to do it. What's there that make us so powerful in learning? Obviously, it's memory. It's not that I'm learning from day one, it's from the day I was born that I'm learning. There's a knowledge base that is developed in my brain. And because of that, I'm able to use information from so many other tasks and quickly bind it to the task, whichever it is required. And obviously, we are very good at predictions. We know that if you move the X this side, that wood will cut that side. Although we have never done this task, but our brain is so much, well trained that it can do predictions, and we do predictions all the time, and that gives us a power over the machine, the learning power. And we want to do something like this even with machine learning. Let me move to the another current practice that people follow. Suppose this is the ImageNet dataset, and this is trained on a network, and it predicts over 1,000 classes. Now, you this is your popular VGGNet, ResNet, or DenseNet, whatever you say. And now you come to your office, and they ask you, okay, you got to train a zebra versus horse classifier. Now, what do? You simply take a pre-trained network, say ImageNet, you chop off, say, for the last layer, you just get rid of the last layer, and then you fine tune and mold your network as per your requirement, and tada, you have your two class zebra versus horse classifier. And there's a name for it. This is called transfer learning. But today, although you will see that there are a lot of interesting names out there: transfer learning, unsupervised learning, supervised learning. But I would also like to point out that we should not get lost in these names, rather understand the essence of what they are doing. So if you see there, they're able to learn the representation and transfer the representation to the new task. So that's what they're doing. They're just like us. From one task, we are able to understand the representation and apply it to another task. That's what's happening here, and that's what happens in most of the learnings, like meta learning or few shot learning. They are some kind of trying to figure out how to learn better representation and how to use it to different tasks. So this is another there are some successes of transfer learning already. So this is RCNN. This is object detector. And uh, and guys, you can if I'm going a bit fast, you can tell me I'm okay, right? And I'm audible and making sense. Yeah. Okay. Because I yeah, perfect. Yeah. So yeah, cool. Yeah, yeah, cool. Ah, great. So let's get to the success of this transfer learning, because we, like, this is bread and butter of the industry or any such thing. We just do transfer learning all the time. And in order to even develop state of the art, say, object detection model, people somehow did some kind of transfer learning with a base pre-trained ImageNet networks, and they're able to get good object detection networks. Then with the same transfer learning approaches, they're able to do state of art scene segmentation or human pose estimation. So that is the success of transfer learning. And why it works? Because of the inherent deep learning network that we use, which is kind of layered. And when I say layered, I think everyone must be knowing that deep learning learns features in hierarchy. And most of the tasks that we see in the real world, there's some kind of there's some kind of constitutional, like a bigger object is made of a smaller object is made of parts, and parts is made of edges. So with the basic constituent, this basic constituent spread across different objects, they spread across different tasks. And with this essence, we can use this kind of transfer learning approach, because the basic knowledge base remains the same, just the top task varies. And yeah, it has been pretty successful. We have been pretty successful in achieving this. And yeah, and this graph is also pretty old, but still I would like to show you. This is from Andrew Ng, NIPS tutorial. So there in 2016, he predicted that transfer learning would be the driver force of the commercial success, and it has proven it to be. But now we feel like, okay, things are working fine, but there are scenarios where the data are not available, and there are scenarios where we need, rather than just simply simple training, some smart way of training. In that scenario, I think it's a good time we should explore other areas like unsupervised learning, meta learning, and so on. Now let's take one more example. Okay, so when I show a child this one, okay, and I'm not asking the child to, I'm not binding this information, the information which is present to the slide, to any task. I'm just telling the child to observe this. He observes a falling apple, he observes a falling ball, and a falling locker. And just by observing, without binding to any task, he was able to understand not only the property of the object, the permeability of the object, the gravitational, the physics governing the falling of the object, that this will break, this will bounce, and this will maybe put a dent in itself. And just by observation, so much of information was gathered by us. And this is the reason that without binding to any task, we are able to store and retrieve information and then use it as such. So that's the idea. Let's how we can incorporate the same thing in our machine learning pipeline. So we know the good mantra is that we should be learning and reusing good representation and good features. Okay, but as of now, as I said already, whenever we have to do any representation learning or whatever, we kind of bind it to task. So even in the image net, that whose pre-trained nets we used, we bind it to 1,000 class classifiers. Okay, we always bind it to some kind of task. Can we, make it task independent? So here we see it's a very strong supervision. There is a one-to-one mapping between the input and output, and they are they're task dependent, and still they require a good amount of fine tuning to perform on your, say, custom task. And one major caveat is they require label data, okay, which may not be easy to get every time. So are there any alternative to this strong supervision? It happens there is, and one such is self-supervised learning. So let me just go to this self-supervised learning. So this is slides from Professor Zizerman presentation. So there's the definition. So why do we need a self-supervision? As we know that there is expense of producing a new data set for each new task. And obviously there are many scenarios, especially as, for example, say medical data, where it's hard to get data, and even if you get data you need expert to annotate it, which may be a bit costly. And this is one of our experience. So there are companies who annotate data for you. So one in order to annotate few amount of data, they charge even tens of thousands of dollars. So yeah, it could be very expensive at times. And another a good reason why we should use self supervision is we have a huge amount of unlabeled data. And this is one instance in where in Facebook nearly 1 billion images are uploaded per day, and in YouTube per minute 300 hours of video are being uploaded. So much of data. And why we should bind ourselves to labeling all the time? Why can't we just tap the data and learn from it? And obviously, the humans example, how do we learn? We never bind it to some task. So, formal definition, it's a form of unsupervised learning where the data provides the supervision. So, we can keep one part of the data as a task, another part of data is its label, and then we can make it learn so that the network is forced to learn the semantic representation. We'll get to examples, and then it will make more sense. So, in self-supervised learning, again, I have personally not worked much in this field. It's new field to me as well, but I'm presenting here because of the scope that I feel is it's humongous. And so these are some slides from Professor Zizerman lecture, and I'll put a link to it. You can watch it. It's really nice. So in his lecture, he has presented these three approaches of self-supervision, and let's go one by one. So first, let me take to the images. So suppose if we have a data, say a cat classifier, and you don't know it's a cat. So what you will do, you can simply do a relative positioning self-supervision task. That is, you take an image. It's not necessary you know its label. So divide it into 8 patches. You take a center patch and you take any random patch, and you have to predict what is the position of that random patch with respect to your base patch. That is the task. Okay, so if you see in training perspective, it will look something like this. Your X will be pair of your base patch and then any random crop, and your output has to be the position. Say this 3 is the position for this patch, and this is the output for this task. So you can simply construct this kind of self-supervision task, and you can just simply train directly from your data rather than sitting down or looking for labeling. So this is a pretty simple example, but there will be data from say space or from other engine systems where you will not be able to make sense of it. And in that scenarios, if we can use self-supervision, it's going to help us a lot. Yeah, and this is another example. Say you have to predict this question mark box with respect to this blue bounded box image, and what the authors propose is that in order to predict that this red patch is at this location, it has to understand the semantic of the image. So the task that we assigned to the network was to just predict the relative position. But in the quest to do that, what it's going to do, it has to learn the semantic features, because unless it understands how a bus looks like, it won't be able to say that, this patch is relative, it's on the bottom, bottom right to this center patch. So although we didn't, did labeling, but we were able to achieve our learning of semantic representation. And what author they did next was, so they give some random patch, and they have these different approaches. And with relative positioning, they were seeing that they use a KNN to find the nearest neighbor patch, and they're able to see that with relative positioning, they learn good semantic features, and they're able to find the patches looking similar to the images. And this is a random initialization. Well, it will not work obviously, and this is a pre-trained image net. So this was showing that with self-supervision, we can learn good semantic features. And they try to apply this on a Pascal VOC detection data set, and what they observed was this is a pre-trained image net which was trained on millions of images, and this is the relative positioning which was just trained with the data set itself without any label, and this is without any pre-training. So obviously you can see we have some kind of boost up, so which encourage researchers to further look for different approaches. And this is another approach which is called colorization by Zhang et al. So here this again the self-supervision task is that you will be given, say, a non-color image, and you have to predict a colored image, as you can see in the images below, and in a hope that it learns the semantic features. And one task that they designed for this was that they took the L channel of an image as input, and the model has to predict the A B color space. And this, so one part of the data, as the definition of self supervision says, becomes the input, and one part of the data itself becomes the output. And this is a cool video of the same colorization approach. When they apply it to a grayscale image, you can see how the network gave the color to different regions. Now it also proves that the uh, model has to learn the semantic features, because then only it can know that it need to color this one as black, or this one as this kind of fiery color. And there is a link here, you guys can go, there are cool demos, you can just have a look at that. Yeah. Cool. Now, what the authors did, they also have this picture where this is the input, this is the ground truth, and this is the output. So the model was able to, correctly color this with some kind of jitter around, but that's fine. And then they took this checkerboard image. This was the ground truth, and in the output, it was not able to color it. So what they said was, maybe it's not like it's learning something from the color signal alone. It is trying to learn the semantic features as well. And in order to prove this, they use three tasks. They use classification, detection, and segmentation. And what they found, like in the class, this blue color is their colorization approach. With this zero means random initialization, and this is initialization with the ImageNet pre-trained. So what they found was, with their colorization pre-trained, they're able to get good performance in segmentation and classification, which clearly suggests that if it was able to do segmentation, it's somehow learning the semantic features of the image. Okay, now let's come to another uh, supervised self-supervised task. It's rotation, and I'm showing you different tasks which I came across, so that you get some idea how to use that in your work. And it's not necessarily that whatever I'm showing you will work for your task. So in our case, we tried rotation, it didn't work. So in that case, you have to come up with your own, say, own self-supervision task. But the idea is you get an idea of how what the people have tried out, and maybe you can then think of better. So that's another one. This is called rotation. Now this is pretty simple task. Yeah, what you have to do is you take an image, you don't know its label, you need not know its label, you just rotate it in varying degree, and ask the network that your task is to predict the degree of rotation. That's all. That's the task. And this is the network that they use. So a 0 degree, a 90 degree, a 180 degree, and a 270 degree, and the model has to predict labels as 0, 1, 2, 3, right? And in this quest, they were still able to learn some kind of semantic features, and which was presented in their table. So this is random initialization 43.4, this is relative positioning, this is colorization, and the rotation achieved 54, and this is a pre-trained ImageNet, which obviously is a little better. Now I'll introduce two terminology for self-supervised learning. So the tasks that we use for self-supervision, the tasks that we design, those are called pretext tasks, like the one which I showed as a rotation. And the main task, say your zebra versus horse classifier, that is called a downstream task, right? So now so they have used like one transformation, rotation. Now further in another paper, what they suggested, why just constrain to one pretext task? Let's do multiple pretext tasks. Rather than just giving rotation, we will do rotation, we'll do brightness, we'll do contrast, we'll do saturation, we'll do sharpness, and we'll do solarization. And they are going to feed it. So here, this example of two, rotation and solarization, but you can plug in different pretext tasks as well. So there will be input, you will rotate it by some degree, you will provide some kind of solarization, and there will be branches to predict each of the pretext tasks. So this will be predicting how much the image is rotated, and this will be predicting how much it's solarized. And again, the goal is that this F, the network, learns the semantic feature whilst doing that. Okay. And this one I would like to this paper is published on March 2020, just a month ago, and this has become the state of art in self-supervised learning. And this is a pretty simple idea. What they are doing, they are taking an image, they don't know its label, it's fine. They are doing some kind of augmentation, say cropping, colorization, and then they are passing to another network. They are learning its representation, and then they are trying to maximize or minimize the agreement between the feature representation. So if the augmented crop comes from the same image, it should attract, it means the distance should be minimized, and if it's coming from different, it should repel. That was a simple idea. And they tried out, different kind of augmentation, as you can see on the screen. And apparently they found out that, random cropping and random color distortion was working the best. But again, for your task, maybe you had to try other approaches as well, so you can do that. And this was their plot, which in the SimCLR was able to even perform better than the supervised learning when trained under some constraint. So this star that you see is pre-trained with SimCLR self-supervised, and this is the what do you say, ImageNet, but it was without any pre-training, and it was able to achieve good performance, indicating the potential of this kind of self-supervision. So that was a few things from the images side, and I would request, like, I'm just kind of presenting an introduction. Okay, I'm not going deeper, but you obviously, as per your interest, you should obviously delve deeper and see if you can incorporate this, because these are very small tricks that you can implement from day one when you go to desk. So it's not a big architecture change that you have to do. And those were some self-supervision tasks in the images. Now you can also create some kind of self-supervision task in the videos, and this is one such paper where they do a shuffle and learn. So here what they have to do, they will be given a sequence of frames, and they have to find out whether it's in the correct temporal order or not. Okay, so for example, these three sequences, these were taken sequentially, so they are in the correct order. It says yes, it's right. But this two sequences, this and this one, sorry, oh, sorry, this one and this one, they are taken with a one frame gap, and it has predicting that it's temporally incorrect. And again, the goal is, in this context, in this quest of identifying the temporal order, they're able to learn good representation. And they created positive and negative tuples out of the video. So if the sequence of frames are in correct order, they call it a positive tuple, and if they're not in correct order, they call it a negative tuple. And then they feed it to this kind of network, and then they again concatenated it, got the features, and they're able to say it's correct or not. And this was the task pretty much. And they also did something like, they have this query frame, and with this they requested that what is the nearest neighbor frame to this query frame. And you can see this was the pre-trained ImageNet, this was the shuffle and learn, and I think this is the random. Yeah, so you can see it's learning good features. And same is can in the case of the second example. Okay. And they also did some kind of test on UCF 101 action recognition dataset. And what they found was, with this kind of pre-training on the videos, they could boost up the accuracy from random to this pre-train to 50.2. So that was really good. And another type of research they did was learning the arrow of time, where they have to identify whether the video is being played in the forward or in the backward direction. Okay, so your positive training samples will be video clips playing forward, and negative training samples would be video clips playing backwards. And again, the authors, they pointed out that in the quest to do this, it's able to learn good semantic features, it's able to learn the direction. And again, if you see the real world, there is so much information besides just the visual cues, the air resistance, the gravity, and so many things. So the idea is that from the videos there are some such information, such as flow, which is being captured. So the network should even capture those kind of informations. Okay, so they were able to identify this kind of ordering. And then, yeah, as they also pointed out, that they have to understand even the gravity, say physics of the real world scenario. So if the water is falling, obviously the water will fall. That's the physics. Like, it if the video is be playing upward, the model should have that kind of understanding that it's against the law. It cannot go, the water cannot go upward unless it's, yeah, some kind of black magic or something. Right. And this another task. What they tried out is video colorization. Again, you have to give they give a reference frame, and the goal is that it has to put color to different frames, and it was doing pretty good. And another self-supervision task that I saw in their lecture was from videos with sound. So objective was that we'll use vision, like the images and the sound together, to learn features from each other. It's like a co-supervision. So they defined two kind of proxy task or self-supervision task. One was to predict the audio visual correspondence, that this part of the audio is corresponding to this image, and another is to predict the sync as well, that this part, the tune that is being played is, sync with the image. So this is the positive sample. So this is the beat, drum beat at this frame. So if you take this snippet, that becomes the positive sample. And if you take this snippet, so this beat is coming from the drum and the image is being showed from the guitar. So that's a negative sample. And then they train this frame and the audio, and they're able to again learn some kind of features and see the agreement, whether the audio or the images were corresponding or not. And in the quest, they again were able to learn good image and video features. Now you can go and have a look at this paper. There are so many other details. Again, I am not in a position now to mention all the details, but yeah, you will get a lot of insights from this paper. So, what can be learned by watching and listening to videos? We can learn good representation of visual and audio features. We can learn the intra model retrieval. Like so, image is one mode of information, or audio is another mode of information. So can we let me show the example. So uh, yeah, so this is what I'm talking about. So image is one mode of information and audio is another. So they'll just give an image frame, and they'll be able, with the learned audio correspondence, they'll be able to identify that which audio should be retrieved based on this kind of image. And they're able to even localize based on the audio. Say a flute and a keyboard is being played, and based on the audio features learned, they're able to localize it. Okay, if the sound is of a keyboard, then the keyboard belongs here. If the sound is a flute, it belongs here. So that was pretty interesting to whatever they did, yeah. And they were also saying that they can use it for, say, syncing of your uh, lips with the voice, especially in the TVs. We see that sometimes the audio and visuals are not synced. So this kind of retraining task, or the task whatever they perform, can be used for such things as well. Right. So that was a quick introduction to self-supervised learning. So what takeaway I want for you guys is that uh, try to use self-supervised learning for pre-training with pretext tasks, especially when you have unlabeled data. No need to wait for it to be labeled. You can directly use the uh, uh, unlabeled data. And also when you have labeled data, maybe you can try out, assume that they are unlabeled and design a pretext task, and just see if they're able to learn good representation and use that pre-trained model for your retraining. Okay, so use that pre-trained model for your downstream task. And as I again pointed out, you may need to define your own pretext task if required, depending on the problem that you are trying to solve. Cool. Okay, now another thing I would also like to highlight is the active learning. It's a case of, I just need some water. Sorry. Yeah. So this is one more thing that I wanted to point it out today is it's another kind of semi-supervised learning. But let's see, what does it mean in essence. So I would always say, don't get lost in the names. When you open it out, it's the same thing, just learning the good features, trying to link it with tasks, and as such. So yeah, this is one good example. So yeah, I think many of you would know this last minute preparation, getting expert just last night before the exam. So I'll give you a scenario. Yeah, so you have just one night before the exam. So what are you gonna do? Are you gonna study, say, chapter 1, chapter 2, chapter 3, chapter 4, or you're just going to study important questions from all the chapter? Any guesses? Or from your personal experience?
Important questions.
Wow, that's very good answer. So,
1%. 1%.
yeah, oh, Ashdeep say he will study nothing. And Paras say he will study last year question paper. Wow, interesting. But the but you saw the what I want you to observe here is why we do the second part, important question from all the chapters, is that's the most from which we can gain. That's the most. Suppose you consider exam as our learning task. That's the most we can score if we study the important questions, right? Rather than just going passively through the entire chapter. Now, if you have say 365 days and you are studying 365 days, that's your supervised learning. Here it's days and there it's labeled data. And one night it's here time, but in your data scenario it's less labeled data. So when you have less labeled data or less resource, you should choose wisely. So that's what active learning is. You should choose which samples to learn from, which questions to study. You may not succeed, directly state of art, but with just this one night study, if you can get even 75%, that's good enough. Yeah. So let me explain this through this machine learning diagram. Say you have this data of a green square and a red triangle, and now you know that it's a classification problem, but assume that you don't know its label. Okay, you don't know that it's green and red, and it's unlabeled presented to you. So what you will do, maybe you just do some kind of randomly sample the images and you label it. When you do that and learn a classifier on it, you will see that you will learn a classifier which is not that great, and it's biased toward the green color line. And also if you see whatever the samples that you chose, okay, they're pretty easy samples, they're far away from the boundary line, so it's not very tough task which will help the model to learn. But if you use active learning, what it will allow you is it will give you this kind of important samples that gets the maximum learning. So where we can get maximum learning, obviously at the boundary cases, because boundary cases are the one where the model struggles. If it's on the edge cases, it's pretty sure it's by default that you know the answer, but the edge cases are the one that trouble us. So with the active learning, you can get these important samples, and with that, with less data and less training time, you can achieve a better model. So the idea is pretty much like this, and I think this you can obviously incorporate in your daily pipeline, because what happens, say for this example, you get a tank versus a yacht classifier, and you have unlabeled data, and you have a budget just to label 6 samples. Okay, that's your budget. So here if you see passive learning, what we do, we simply label everything and we just give it to the network and it has to learn. But in active learning, what we can do, we can initially say label 2 samples, we'll give it to active learning, and let's call this as learner, and we'll ask this learner that you suggest me which samples that I should label next, because you have budget of just 6 samples. So the learner will say, okay, I think these samples are important, you should label this and give it back to me for training, then I'll retrain it and I'll get a better performance. So that's the idea. So this is what we'll do. We'll say select some samples, we'll label it, then we'll pass all our unlabeled samples to the data, and the model is going to tell us which is the most informative samples that you need to label and give it back for retraining. But the question is how the learner knows that these are the important samples. Yeah. So there are strategies called query strategies for this. So yeah, and this whatever active learning things I'm presenting to you, okay, this all I created, but the concept and all, it's very nicely elucidated in this Stephen Hosen blog. So I highly recommend just go and read his blog. It's pretty much what I'm stating here. So what he says is that active learning can be thought, and it's pretty right, yeah. Active learning can be thought of as a type of design methodology similar to transfer learning, which can also be used to leverage small amount of label data. So just think kind of a design which you can incorporate in your daily training. And the main hypothesis in active learning is that if learning algorithm can choose the data it wants to learn from, it can perform better than traditional methods. Okay, so there are 3 main scenarios of the active learning. So one is called, say, membership query synthesis, stream-based selective sampling, and pool-based sampling. So what happens in the first scenario is there is a learner, and it identifies that, okay, these are some important samples. So it will suppose what it will do, it will generate itself that instance. For example, you are learning, say, horse versus zebra, and all the zebras are in the left, looking on the left, and it identifies that maybe if zebra is looking on a right side, then that will give more information, the network can learn better. Then it will generate itself those right instances, and then it will ask you that maybe you can label this kind of instance. And then another approach is stream-based selective sampling. So here we assume that we have lots of data. So we take a sample, we give it to the learner, and we ask, do you think it's important? And if it says okay, it's important, then you label it, and or else you just discard it. And this is the most common that people use in practice. Well, they use many things. I haven't researched extensively, but this is one common thing that I saw with my short time of research is pool-based sampling, where you will be the learner would be given a pool of a batch, say a batch of unlabeled instances, and then you'll ask a learner, "Hey, learner, what do you think? Or which samples should I label?" Then the learner would rank all these unlabeled samples, and based on this ranking, that you can choose the most informative samples which you need to label it. Okay, so I have been talking about information like the learner based on some kind of information decides that which labels are important. So what is the strategy that it uses to ask for labeling? That's query strategies, and this particular approach falls under uncertainty sampling. And what the concept is, suppose let's take this example. Okay, so there are two instances, so d1 and d2, and it's a three class classification problem. And the prediction from the network from the learner is label a 0.9, label b 0.09, and label c 0.01. And for the d2 it's same 0.2, 0.5, and 0.3. Now one query strategy that you can use is called least confidence sampling. Now the idea here is that whichever first of all, whichever instance the model is unsure about, those models are important because those are the tougher samplers which model need to learn rather than learning the easier sample. So what it's going to do, it will select those instance for which it has least confidence for its most likely label. For example, for this instance, the probability for label A is zero point 0.9. For this instance, the probability for label B is zero point 0.5. So for in the second instance, obviously it's label B, but its probability is zero point 0.5 compared to zero point 0.9. It's unsure about this, so it will select D2. So that's one strategy. The next is marginal sampling. Now this you have to understand that sometimes what happens is a class may look similar to two different classes. Say I take a horse, and some of them maybe they look like zebra, some like horse. So it may predict say a horse as zero point 0.6 and a zebra as 0.35. So we cannot discard that uh, second probability. That's where marginal sampling comes in. What it will do, it will take the smallest those instance for which the difference between the highest and second highest probability is least. So here highest is 0.9 and here 0.09. So it will be something around 0.8 or something. But here the difference will be 0.2. So since the difference is less, here it's confused about these two classes. So if it's confused means obviously those are tough samples. So it will take D2. That's marginal sampling. And then there is entropy sampling, which kinds of incorporate all the probability. So entropy, it comes from the information theory, where suppose take a class A and class B. So if you are 100% sure that it's class B, then the entropy is zero because there is no information. You already know it. There is no uncertainty. But if it's class A zero point 0.5, class B zero point 0.5, then you are not sure about it. There's the maximum information. So the entropy sampling kind of computes the entropy, and for those which it will be most confused about, that will have the highest information. And again, in this case, it will be D2. So these are three of the maybe there are many more strategies that you can look upon in order to query important samples. Okay. Now to present the whole pipeline, suppose if you have this data set D1, D2, D3, D4, D5 with some features A and B, what you will do is initially you will select some small amount of labeled data set. Say you selected D1 and D3, and that's your label Y and N. And this is your unlabeled data set D2, D4, and D5. Now what you'll do, you simply train the model. Now once you train the model, you get the output prediction. And the uncertainty sampling that we discussed, for example, say least confidence sampling, based on that, you will select the samples. So suppose we want to select just two samples, then we selected D2 and D4. Now you are left with this unlabeled instance. Now again repeat, again train the model, again choose the unlabeled instance. So you can kind of play it in a loop till some stopping criteria is defined. So stopping criteria could be your accuracy is not improving, or you are exhaust of your budget that you can spend for labeling, or maybe yeah something else as well. You can just define it. So this is pretty much the idea. And yeah, again, just to summarize it, gather the data, split it into seed and unlabeled data set, train the model, choose the unlabeled instances, then repeat step 2 and 3 until some stopping criteria. Okay. And the takeaway is, yeah, try to incorporate this strategy in your training pipeline rather than just relying on just taking the label data and passing it to supervised learning. You can also use pre-trained that we discussed, the self-supervised pre-training, and perform active learning on that. And we hope that maybe we get output, but a much better, efficiently trained supervised model with this approach. Cool. Yeah. Now, one last topic that I wanted to quickly introduce is this few shot learning with meta learning. So first of all, you might be knowing the few shot learning means, as the name suggests itself, learning from few examples. Okay. So this, again, coming back to this example, here we just use 3 instances from each classes. So just 3. So that's a 3 shot learning. But in literature, you'll see the terminology is also known as K-shot learning, and the most popular ones are 0 shot learning, 1 shot learning, 5 shot learning. And I think the name themselves imply how many number of label samples they will use. And in our example, it's a 3 shot learning. Now, why do we need a few shot learning? Because deep neural network, for example, ImageNet, they require a lot of data. They take longer time to learn. So if there is a strategy, if we can learn from smaller amount of data, obviously it will save a lot of our resources and will be at a lot of benefit. And then there will be many applications where it's tough to collect data. Okay, many critical application in industry or other, say, medical, where it's really tough to perform experimentation to collect data. And obviously, we most of the time we'll have unlabeled data, but labeling are expensive. And also, if you have to train new task, you have to retrain it, you have to fine tune it. And and in scenarios where the new tasks are updated frequently. For example, say face recognition. There you train, say, a 5 face classifier. Now again, when new face comes, again you need to retrain it with 6 class classifier. But here, and if the new person comes in, maybe you don't have enough images for that. You have just 1 or 2 images. So in those scenarios, you can use this kind of training. So people say the terminology used here is n-ways k-short learning, if you see in the literature. So n-ways means number of classes, and k-short means number of samples per classes. Again, no need to go in the technical terminology, just understand the essence, and yeah, that's fine. And there are a lot of this whole different domain of research going on in one-shot learning or few-shot learning. And there are so many approaches developed, like Siamese network, matching network, prototypical network, memory augmented network, or meta learning. So one approach which I would like to highlight today is meta learning, because it's very interesting, and I was pretty excited when I first came to know about it. And what happens actually is, here 2 level of learning takes place. So I'll just quickly go through it. So instead of when we do a normal kind of learning, what we do, we just train it on one task. Say you want to make a zebra versus horse classifier, we train it, that's all. But in kind of meta learning, we'll train it on multiple tasks. Okay. And the goal will be that when the model is trained on multiple tasks, it somehow become competent enough to solve any new task. And if it's experienced enough on so many multiple tasks, whenever any new task comes in, it will not require that much data to solve that task. Say you learn cycling, you learn bike, you learn car, then maybe you will require very less time to learn driving truck, because you're trained on so many tasks. So that's the idea. And this approach of 2 level learning, where we are learning one task and then we are learning overall, is called learning to learn. And one example I would like to give here is, for example, again, when you study for your exam, say for math exam, you are learning some strategies in math. When you learn for history exams, you are learning some strategies in history and chemistry as well. But overall, there is a learning going on across the task. For example, from all these approaches, you learn that, okay, if I make a note, a formula note, or a history chronological order note, I can learn better. So in the quest on learning on different tasks, overall, you learn some strategy which enable you that any new task come, you can quickly learn on it. That's the idea. And how the pipeline looks like. So suppose this is your traditional learning data set. What we do is we divide it into a train set and a test set, and then we train the network. But in case of meta learning, what we'll do, we will divide it into tasks. When I say task, for example, when you consider classification, so classifying uh, a horse and a zebra would be, say, one task, classifying cat and dog could be another task. So in that scenario, And instead of taking the data set, we take the task as training task and testing task. Okay, I think I can show you with better figure, but I'll come to it. But I would like to highlight again. So there are a good amount of research going on in this area as well. So there are benchmark dataset like Omniglot dataset, Mini ImageNet, and MNIST, which people try on. And this is very popular dataset, the Omniglot dataset. So this is so there are handwritten say characters from 50 different alphabets. So when I say alphabets, means English is one alphabet, Sanskrit is one alphabet, and inside every alphabet there are so many characters. So within 15 different alphabets, there are 1623 characters, and for each characters we have 20 samples. Okay, so this data set is also called as a transpose of MNIST, because in MNIST we have few classes, more samples. Here we have more classes, few samples. And this is the idea that with just few samples can it learn across different tasks. Okay, and that's why this data set is so popular for the future learning. And then there is Mini ImageNet, where instead of 1000 classes they have taken 100 classes with 600 samples per class, and they have divided into 64 class for meta training, 16 class for meta validation, and 20 class for meta testing. Okay, and this is a really good paper I read, Model Agnostic Meta Learning for Fast Adaptation of Deep Network. This is 2017 paper, which proposed this kind of one kind of meta learning, model agnostic meta learning, but there are many such papers built up on this. So I will just tell you how this task things work. So suppose this is your data set, okay? uh, and your task is 10 class classification, and when you're doing normal learning, what you will do, from all the 10 classes you will get some samples in the training set, and from all the 10 classes you will get some samples in the test set. That's what is your normal practice, and then you train it. Okay, but when we come to meta learning, for example, if you have a task of classifying 60 classes, so you'll split it. Each class, assume that as a task, so you'll split it, and 40 classes you will put it for training and 20 classes for testing. So by doing this, you are ensuring that when we are testing this meta learning network, we are ensuring that it's not seeing the class which is it is already seen. It's totally independent task. And within this 40 class, we design tasks. Say the 10 class, classifying between 10 class could be one task, classifying between another 10 class could be another task, and so on. So this way, we have this data set, but we kind of make it like distribute it over tasks, and which ensures the model that it learns in a better way. So yeah, this diagram I draw just to again give you some insight of the terminologies. So this is your say meta train, and this is your meta test, and inside this you'll define into different tasks. So this could be say 5 class is one task, another 5 class is another task, and in every task is managed by a model which is independent of the task. Okay, and you need to further go and research on it and see how it can help in your daily work. Now let's see, this was the task distribution. Now let's see. Okay, I have 5 minutes left. Okay, so let's see uh, how we train this kind of network. Okay, so this is the normal training. So what we do, we have a train set. We'll do some kind of batching, X, Y, and then we'll put it to forward propagation. We'll pass backward propagation. We'll compute loss. We'll use this gradient update. We'll train it. And once the model is trained, say it was f theta, it become f theta hash. Then we take the test set and we compute its performance. That's our normal training. What we do in meta learning, so suppose this is your meta train data set where you have different tasks, a 5 class classifier task 1, a 5 class classifier task 2. So you will take task 1, say the first task, and you're going to create a copy of this model which you have to learn. Okay, this is a copy of this model. And then you take another task, say T2, and you are going to take another copy of the same model. Okay, it's clear up to here. And what we'll do now, yes, this is the copied model. Now from this first task, we'll take this training data set and we'll train this network, okay? And then the training is pretty normal. It's the normal gradient descent. And then we'll take the second task, and again we'll take the training set of the second task and train the second model on the second task. So this network has learned to optimize on task 1. This network has learned to optimize on task 2. Okay, fair enough. Now what we'll do, we have this train network for the task 1, f theta bar, trained on task T1, and f theta bar again trained on task T2. now will take the test set from this task and computes its performance, its loss, whatever. And same will take the test set from the second task and computes its loss, performance, and whatsoever. And now based on the loss that is computed from both the task. So here it was learning within the task. Now here it's learning across the task. It will do another update, say a second update with beta learning rate, summing over the loss of different tasks, and it will finally update this original model. Okay, and this formula is again for the updating of this inner loop. So there is two level of learning going on. One is within the task, the inner loop, and one is outer loop across the task. So by doing this and by back propagating, these parameters are tuned to a value such that they are able to perform well on different tasks. And when they're able to perform well on different tasks, it means, yeah, you're able to, learn. They're able to learn quickly across different tasks with just few iterations. Okay, and you will, yeah, this is a formal algorithm from the paper. I'll just quickly go through it. So they say that you will have a distribution of a task, and you will have two learning rate. Alpha is for the inner and beta is for the outer learning rate. You will randomly initialize your parameter, and unless your some stopping criteria is done, you sample batch of tasks. In our case, we took two tasks, and for every task for their training samples, we uh, compute the loss, we compute the gradient, and we update that. Okay, theta hash. That is for that task. Okay, and do it for every task. And after, say, for two tasks, what I did, I took an average of, I further computed the gradient on the test task, and then on the outer loop, I'm updating this final network. Okay. So again, not only paper, you can also refer. There are some good blogs out there to explain all these concepts. I have this link, for example, AI gradients. So yeah, it's not always that the papers will give you all the information. Blogs, videos. There are a lot of people, contributing as much as they can in all the community. So you can refer those as well, and you can get a better insight. Again, the idea here is at the end of learning of the task, so the theta will reach at this position such that whenever it's subjected to a new task, just with few gradient updates, it can update to any, it can, generalize to that task. This diagram actually better explains. So for example, you have to do perform on task 1, task 2, task 3. If you are not using this kind of meta learning, then it will take really long time for you to learn. But when you do meta learning, the parameters got tuned in a better initialized position, like this theta. And from this, in order to optimize for the different tasks, it's very easy, like it's very quicker compared to the left one. So that's the idea that this network does. Okay, and these are some it's 6 o'clock and I'm on time, good. And these are some references. It's not in that proper order, but yeah, maybe I have to add few more. And yeah, besides this, I'm a failed YouTuber. I upload sometime my learnings on YouTube. And yeah, the first video was uploaded in CSIO lab itself, and Devinder, Arshdeep, they were the first subscribers, and I haven't succeeded in that. But again, I do that, whatever like information I get, I try to post it sometime. Then I try to write sometime blogs on whatever things I learned, so you can have a look. And these are some of my yeah links. And yeah, thank you so much for listening me for an hour. And yeah, we are in tough times, so contribute to fight COVID-19 whatsoever you can, either financially by staying at home, motivating somebody, sharing your food, or using your knowledge. And that's all. I'm done. And yeah, let's see if we have some questions. Thank you so much, guys, for listening. Yeah,
Thank you, Mr. Anuj. And now
thank
the
you.
session is open for questions. So attendees can ask their questions if they have any.
Hello. Yes. Hello, Anuj.
Hi.
Yeah. So thanks for the presentation with a lot of energy.
Yeah, thank you.
Yeah, that's good. So this meta learning part. So can I
Uh-huh.
say that it's a kind of parallel transfer learning? So since we are learning this three parallel tasks, say three
Uh,
tasks are there, and I'm using that learned information for new tasks to adapt.
yes, you're right. You can say it. It's pretty much the same thing. It's a fancier way of transfer learning.
Okay, okay. And one more question.
Yeah.
So when you say this future learning, So we
Mm-hmm.
have a few examples to train, right?
Yes, you're right.
So how do we take care of a problem of overfitting? Means normally we have lots of parameters, so it might
Uh-huh.
fit on using few examples. So how people take
Yeah.
care that
Mm-hmm.
problem?
So that's really rightly pointed out. So you see, when I was doing this training, so for example, in the first task, I have say 5 examples, and when it's trying to overfit, it will do that. For example, it did it, but the goal is that I'm not optimizing based on this task. So if it's overfit, it will not be able to do well on the second task. So there I'll be penalizing with a loss function. So this will force that because I'm training it on multiple tasks, it will force it that it does not overfit to any of the tasks. Rather, it generalizes. That's the idea.
Okay, yeah, got it, got it. And
Okay.
ये कौन से
and
स्पीकर
in
के लिए हेक्टिक हो
industry,
जाएगा एग्जीक्यूटिव
the
मीटिंग
Mm-hmm.
same is our motive remains to
नीचे
finally
वाला स्पीकर
come
एक
up with a product, right?
हेक्टिक
You are right.
So, so which of this learning is more popular, or it's a right way to sell our idea for
सब टट्टल
customers?
हो गया मी लैंग्वेज
Mm-hmm.
So,
So
provide.
मीटिंग ही करवाता रहूंगा क्या मैं बस
yeah, so actually customer doesn't care about what you do. Okay, they just want their product. So as of now,
नहीं करवा
this
ले क्या
project we started
सबको
just
बुला ले
1.5 month ago, because for one project we are not able to
मैं
get
तो
the
लिख
data, and
मैं तो
then
लिखा ही नहीं
this
एंटीसी
project then become bigger, that we'll do something in the small data domain. But as of now, people, as I said, they're doing transfer
11
learning
बजे है
only.
एंटीसी की
Usually they get some kind of label data, they do some kind of pre-trained network, and they sell it.
वही तो मैं कह
And
रहा हूँ
if
अलग
I'm coming to the product perspective, again, this what I have observed,
एडिटर
although
मीटिंग
I
करनी
am
पड़ेगी
mainly on the research side, I'm not on the product side, the same like you guys do. But this part of training and getting it, it's a very small part. On top of it, there are so many other
हाँ तो
stuff
फिर तेरे को
to
बुलाना ना तो
making it
जब 11 बजे का टाइम
productionize,
दिया तो
or
कुछ
there's so
तीन
many
बजे
other
की
pipeline in order to in order to serve the customer, that this becomes a small part. But again, it's an important part.
Yeah, yeah, true, true. Okay, okay, nice, thanks.
Yeah, thank you.
Hello, Anuj.
Yeah, hi.
Hi. Oh, I have a question. Uh,
Yes.
you also taking care of the background of the images during the training of a model?
In which context you are saying?
In suppose in case of real-time image processing,
Okay.
if you have to detect suppose a deer in the
Mm-hmm,
forest
mm-hmm,
environment,
mm-hmm, mm-hmm,
so if the deer is behind any tree, okay,
mm-hmm, mm-hmm,
so before that you have to detect that image that some
mm-hmm.
object is moving there. So
Okay.
here the detection will take place.
Mm-hmm,
Okay. So
mm-hmm,
on which basis the detection will take place here? Okay.
mm-hmm,
Like the movement of tree will
mm-hmm,
lead to the change of the frame. Then you can say that the image has detected.
mm-hmm,
Okay. So
mm-hmm,
it will capture the image of the tree. But
mm-hmm,
but actually our problem was to detect that deer.
mm-hmm,
Okay. So here some background will play some important role. So in this scenario, how
mm-hmm.
you will have problem?
Okay. So again, this whatever strategies you applied to solve this problem, it won't be any specific strategy. So it's problem dependent. So if it's maybe you can say first of all you applied say object detection, but maybe it's getting camouflaged with the background. Then maybe you can try instance segmentation, or you can try some other network. And even if it's not working, then maybe you can try tracking as well. That if it's say you got a picture of the deer, and you over the successive frame it's getting lost in the forest with the camouflage, then it's if there is a tracking model which can predict where the deer is going, in that context also we can detect it. So I am not in a position to give you one fixed answer, so
Mhm.
that will depend on the data itself, but you can try all these ticks and tweaks and tricks to get a final output.
Like if you have a couple of sample images of
Mm-hmm. Mm-hmm.
suppose a few targets in a particular
Okay.
location, you have picked that
Uh-huh.
images and you train your model. But
Okay.
after training that model, can you test with the some the images you acquired from other locations, and it will give the better accuracy? Means it will give the good accuracy.
Well, if you see the theoretically literature wise, they always say that the train and test data should come from the same distribution. But
Okay.
if your model is well trained enough, then it
Okay.
should be like if it has learned good semantic feature of the deer, then it should be able to
Mhm.
do that. And if not, you could try this kind of learnings as well, like the few shot learnings. Suppose if the deer from another scene is totally different, then you can consider this as a new class, and whatever semantic features that you have learned with your previous training, you can use that knowledge on this kind of a new task. As you said, there will be fewer number of samples. I hope this kind of strategy could help you, whatever we are seeing on the screen, like either the self-supervised or representation learning or this kind of say meta learning.
Okay. Okay. Thank you.
Yeah, no problem.
So
Okay, I saw one question pop up, but I could not read it, from Sailesh Mohine. Uh, yeah, hi. Hi, I can hear you. Yeah, hi.
Anuj, is there any specific criteria to select number of input and hidden nodes in the neural network?
Okay, that's that's the toughest question I get. Actually,
I'm little bit confused to how
yeah,
to select the input and hidden nodes in the neural network.
Actually, you need not be confused about those, because like practically there is no such defined rule. It's a network which, for example, say deep learning, it learns in hierarchy. Okay, so the best thing is to go with already designed networks first of all, with whatever their architecture is. Say you take VGG, or the best performing now is fixed SufficientNet or DenseNet. See how their architecture is, because they have done extensive research on fine tuning number of layers through empirical experimentation. Rather, they may have some kind of theoretical mathematics as well, but there is no such concrete mathematics. So I would suggest that you first look into their model and try to replicate their architectures, like how many of those they are selecting, and I think it should perform well. And if not, then from there you start pruning your network, like taking out layer or adding layers. And I mean, that's the best practice actually.
Okay, okay, okay.
I don't have a mathematical
There
answer
is
for
no
that. I'm
specific
really
rule
sorry.
for selection.
And yeah, there is. I don't
Thank you,
think.
Ravi.
I'm not. Sorry, Salish.
Thank you, Anuj.
Yeah, yeah, no problem.
so any more questions from the participants? No questions? Okay. So then we can wind up this session if no questions. Okay. So thank you, Mr. Anuj. And
Thank you.
now we can have a group photograph to make this moment more special for you and for all of us. So kindly stop sharing your screen, and
Okay.
then we all can
Yeah.
get live. Yeah. And we can have a
Uh,
group photograph.
yeah, yeah, sure. But
Yeah.
okay, stop sharing. I got it, and I need to open my webcam.
And I request Mr. Arshdeep also to kindly
Yeah,
come
Arshdeep
on
was
the
not there
screen.
yesterday.
Sure, sure,
Yeah,
sure,
he
sure.
couldn't join us yesterday.
I am
So
in pretty dark light. Am I? Yeah.
no
Wait.
issues.
I'm just
We
kidding.
all are locked down, no issues.
Yeah. Okay.
I request everyone, yeah, we have Mr. Arshdeep also now.
Yeah, thank you, thanks. Aji, where are you? I'm in Bangalore, stuck between us. Yeah.
So let's wait for a moment. Let's let people join in. Yeah,
And
yeah,
how
please,
are
you're
things? How are things in CSIO? Is it the office is working or
No,
it's
no, no.
lockdown present.
Everything has shut
okay?
down.
छुट्टी मतलब हाँ बढ़िया.
Yeah, it's more cooking time and learning. That's why, other than such things.
सरेश सर आज भी ब्लर्ड इमेज है एक बार चेक करो
तो अनुपमा, मेरा जो लैपटॉप है ना, उसमें VGA कैमरा है.
कैमरा में प्रॉब्लम है.
ओके ओके ओके
Oh, yeah, different texture is here.
नहीं नहीं
so
इसके
new
कैमरा
effect in the image
में इंफ्रारेड कैमरा लगा हुआ है.
Can
You
anybody
can
apply
use this
image
image for
processing or
training
deep
the
learning?
model.
Yes, we can use.
and
Yeah,
extract
sorry.
the correct information out of it.
Yeah.
So we are waiting. All of you, please kindly turn on your camera. We can have a group photograph. Yeah, we're waiting. To get maximum participants in. Smile. Thank you all.
Thank you.
So thank you, Mr. Anuj, for a very informative session.
Thank you.
Thank you.
And I
Anuj.
thank all
Thank
the
you, everyone.
participants also.
Thank you, Anupama. Thank you, everyone.
Thank you. See you tomorrow. Have a nice day. Stay safe and stay home. Bye.
Okay.
Thank you.
Bye.
Bye bye.
Bye. Good night.
Bye.
Good night.
Good night.